Welcome to this lecture on linear programming and applications. Today, we are going to explore a fascinating and magical mathematical bridge known as complementary slackness. This powerful theorem connects the physical resources you have available directly to their true economic value. By the end of this video, you will understand exactly how to use it. To understand why this concept matters, before we look at the math, imagine you own a bakery making cakes and cookies. Your goal is to maximize profit using a limited amount of flour and sugar in your pantry. This original decision-making process is called the primal problem. Now imagine a competitor wants to buy your entire bakery and needs to figure out a fair price for your raw materials. This parallel economic problem of pricing the raw materials is called the dual problem. Complementary slackness is the mathematical bridge that connects your baking decisions directly to their pricing decisions. Let us visualize this connection by looking at the mapping diagram on the screen. On the left, we have the conditions of our primal problem, and on the right, the dual problem. The arrows show a strict logical rule. If a primal constraint has leftover slack, meaning a resource is not fully used, the corresponding dual variable, representing its price, is forced to zero. Conversely, if a primal variable is strictly positive, meaning we are actively producing that item, the corresponding dual constraint must be perfectly tight, meaning it has zero surplus. Building on that visual intuition, let us define our terms technically before we see the formula. A slack variable represents the unused amount of a resource in a less than or equal to constraint. A surplus variable represents the excess amount above a minimum requirement in a greater than or equal to constraint. The core rule of complementary slackness is simple but absolute. You cannot simultaneously have leftover resources and a non-zero economic value or shadow price for that exact same resource. If a constraint is not perfectly tight, the paired variable in the opposite problem is forced to be zero. This brings us to the mathematical heart of the theorem. Conceptually, this formula comes from the idea that resources only have marginal value if they are acting as bottlenecks. The formula states that the product of a primal slack variable and its corresponding dual variable is always exactly zero. The vector y represents the dual shadow prices measured in dollars per unit, and the term in parenthesis is the primal slack vector measured in physical units. If the physical slack increases, meaning more leftover resource, its economic price y must drop to zero. Before we prove the theorem, let us see it in action with a concrete example. We are given a standard primal problem where the goal is to maximize profit subject to 3 resource constraints. We are also given the optimal primal solution where x1 is 1 and x2 is 3. We are asked to find the optimal dual variables without solving the dual problem from scratch. We start our approach by calculating the slack for the first constraint. By plugging in the optimal values, we find the slack is exactly zero. Continuing our calculations, we plug the optimal production quantities into the second resource equation. We find that its slack is also exactly zero, meaning the second resource is completely exhausted. However, for the third constraint, our calculation shows we have 1 full unit of resource left over at the end of production. Because this third resource is not fully utilized, the strict rules of the complementary slackness theorem dictate that its marginal value must be exactly zero. Therefore, we immediately know that y3 equals 0. Now we shift our attention to the primal variables to find the remaining dual prices. Since the optimal value for x1 is strictly greater than 0, complementary slackness dictates that its corresponding dual constraint cannot have any surplus. It must be a tight, strict equality set equal to the profit coefficient of 3. The same logic applies to x2, giving us a second tight equation. By substituting our known value of 0 for y3 into the first equation, we simplify our system to 2 basic linear equations. We solve this simple system by subtracting the second equation directly from the first, which immediately gives us y2 equals 1. Substituting this back into the second equation gives y1 equals 1. We have completely derived the optimal dual solution without ever running the simplex method. Physically, this final answer means that acquiring one more unit of the first or second resource will increase our total profit by exactly $1, while acquiring more of the third resource will not help us at all. Let us look at another powerful application of this theorem, verifying if a proposed solution is truly optimal. A student proposes a solution to a linear programming problem where x1 is 10 and x2 is 0. We need to determine if this is correct. We will assume the proposed solution is optimal and use complementary slackness to find the corresponding dual variables. We start our verification process by checking the slack in the first primal constraint. The calculation shows it has exactly 0 slack, meaning the resource is fully utilized. Next, we check the slack in the second primal constraint using the proposed quantities. The calculation reveals a massive slack of 8 units, meaning 8 units of the second resource are left sitting idle. Because there is leftover resource, the theorem strictly requires that the corresponding dual variable y2 must be 0. Furthermore, since the proposed value for x1 is strictly positive, the first dual constraint must be a tight equality. Substituting y2 equals 0 into this equation gives us y1 equals 2.5. We now have completely derived the proposed dual solution based entirely on the student's primal solution. To verify if it is valid, we must check it against the remaining dual constraint. When we substitute our calculated dual variables into this specific inequality, we get the mathematical statement that 2.5 is greater than or equal to 4. This is obviously false. Because the derived dual variables violate a fundamental dual constraint, the dual solution is infeasible. Therefore, the proposed primal solution cannot possibly be the true optimal solution. Now that we have successfully used this theorem to solve problems, let us understand exactly where it comes from by proving it mathematically. This first chunk of the proof is setting out to define our starting boundaries. We start by defining the standard primal problem, where our goal is to maximize total profit subject to physical resource limits. We also define the corresponding dual problem, where we want to minimize the total theoretical cost subject to market profit constraints. For both problems, we require that all production quantities and assigned prices are non-negative, because you cannot manufacture a negative number of items, nor can a physical resource have a negative intrinsic value. This sets up the foundation for our derivation. We begin the mathematical reasoning by taking the dual constraint inequality and multiplying both sides by the non-negative production vector x. This preserves the direction of the inequality. Next, using the standard rules of linear algebra and matrix transposition, we rearrange the terms in the middle. The transpose of a product allows us to group the matrix A with the production vector x. This algebraic manipulation is crucial because it sets up the equation so we can apply our primal constraints. By substituting the primal resource limit into the inequality, we establish a new upper bound. This step beautifully translates our physical resource limits into economic value limits, connecting the two problems. This resulting chain of inequalities establishes what is famously known as the weak duality theorem. It guarantees that any feasible profit you achieve in the primal problem is always less than or equal to any feasible cost valuation in the dual problem. The dual cost acts as a ceiling. However, the strong duality theorem takes this intuition one step further for the final optimal solution. It states that at the absolute best, optimal point, the maximum possible profit exactly equals the minimum possible cost. There is absolutely no gap between the ceiling and the floor at optimality. This perfect equality is the crucial foundation required for our next and final step. Because the optimal objective values are perfectly equal, the inequalities we used earlier must actually be strict equalities at the optimal point. By rearranging the terms and factoring out the price vector y, we isolate the primal slack vector inside the parentheses. Similarly, factoring out the production vector x isolates the dual surplus vector. Since all prices and slacks are strictly non-negative, their dot product can only equal 0 if each individual matching pair multiplies to 0. This mathematical reasoning proves the intuition we started with. You cannot have both leftover resources and a positive shadow price. This concludes our derivation of the complementary slackness theorem. We have now covered the full topic of complementary slackness. Let us reinforce the three most important ideas. First, this theorem serves as the ultimate cross-check between a primal linear programming problem and its dual. Second, it enforces a strict economic rule. Unused resources always have a shadow price of 0, and positive shadow prices mean a resource is fully exhausted. Finally, by linking the slacks of one problem to the variables of the other, it provides a rapid way to verify optimal solutions without redundant calculations. Excellent work mastering this fundamental concept today.